Welcome back to the New Stack Agents, our show about all things AI, and especially agentic AI at this point. And we're here at the PyTorch conference. Thanks to the Linux Foundation for inviting us. And I'm here with Suresh, the CEO of Clockwork.
Thank you very much for having me. It's a pleasure to be here.
No, same here. I talked to a lot of your colleagues at Clockwork over the years, so
we're all excited about what we're working on, yes.
Absolutely. I was thinking to just get started, it makes sense, I think, to talk about what Clockwork does today. I want to talk about the history a little bit, but what do you do today?
Yeah, so today, Clockwork builds a software layer that focuses on optimizing the communication between GPUs in large clusters that are then used for AI workloads. As you well know, AI workloads are among the most distributed, the most demanding distributed applications in history. And a lot of how well the workload performs depends a lot on how effective the communication is between GPUs. And so really what Clockwork focuses on is a set of software building blocks that allow you to get three things that ultimately lead to higher AI efficiency. The first is you have deep visibility into what's happening with your GPU fleet, all the way from the network up to the actual application layer, to be able to detect problems and rapidly address those problems. That's the first thing we do. The second thing we do is really focus on how do we deliver fault tolerance such that when you have hardware failures, in particular when network links, for example, disappear, how do you make sure that your AI workloads are resilient to those kind of failures and continue without interruption?
Right.
This is a particularly big pain point for AI workloads.
Because when there's interruptions, you have to go back to whatever the last checkpoint was, Indeed. Wherever you made a backup the last time, right?
Indeed, I mean, it's crazy. When you look at large-scale GPU clusters, typically availability of those clusters runs in the high 80s to low 90s in terms of percentage of availability of the overall hardware. Contrast this with cloud availability, which is often measured in 3 to 4 nines. It's a completely different world. And what's worse is that when a link disappears, you have to, as you rightly said, Frederick, stop the workload, go back to a checkpoint that may be many hours old, and restart your training all over again, right? So hundreds to thousands of GPUs really wasting all the compute that they've already performed.
Right.
That's the second thing we do, is address fault tolerance to failures in the network. And then the third thing we do is look at the network that's carrying messages from one GPU to another and understand when you have congestion, when you have two flows colliding in the network that might cause things to slow down, and avoid those using software. We can do congestion management, quality of service, redirect flows so that they're not contending with each other. So if I step back, really the software platform we built is called FleetIQ. It's focused on ultimately raising the efficiency of large-scale GPU clusters by addressing deep visibility, fault tolerance, and performance acceleration.
Right. It's so interesting to me because when I first talked to your colleagues, now you're new in the position, I should say. You came in March. Is that right?
I joined formally as CEO in March. I've been on the board for a year before that. Yeah.
But when I talked to Balaji and Dan, who were the co-founders, or are the co-founders, early on, what we talked about was syncing clocks and servers.
Yep.
How do you go from that to this, which is very different at a much different level?
It's a fascinating journey for us. So, I think if you look at the history of Clockwork from 2018 up until 2022, the fundamental building block and the core innovation of the company was, as you rightly said, the ability to synchronize clocks within a data center, within a cloud, across cloud regions, across multiple clouds, all using software, and being able to get to tens to hundreds of nanoseconds within a data center using software clock synchronization.
Right.
First 4 years of the company was really a small team that acted almost as an outgrowth of Stanford lab.
Yes.
And so it was 5 or 6 people. Both the core technology and the use cases we were pursuing were all about clock sync. So for example, we have some of the Fortune 100 financial companies using us to synchronize clocks, but then use that for time-stamping financial records, for time-stamping market data, and so on, right?
Right.
In 2002, there was this big epiphany, and that also accompanied a funding round by NEA. And the epiphany was
2022.
Sorry, 2022.
2002. It's like that was a very different time. We'll talk about that too.
2022, we had this epiphany that if I have accurately synchronized clocks, then it's possible for us to measure the time it takes for a packet to go from place A to place B. And that really became the foundation of network telemetry, right? Accurate latency monitoring for data center applications was really what began in 2022. And in fact, one of our largest customers that we've been public about is Uber. Uber is using that ability to look at cloud VMs and cloud containers, accurately understand what's happening within the network, and is deploying us across hundreds of thousands of VMs across multiple clouds, right? Now, 24, I think, is the next big jump in our evolution as a company. While accurate latency monitoring is extremely important for cloud applications, it's critical for GPU clusters. And so we started applying the technology to GPU clusters where we really managed to get extremely accurate telemetry all the way from the network. We were also able to correlate this to what's happening with GPU to GPU communication. So Nickel, which is a communications library, how is the communication between GPUs and the AI training workload itself being impacted by that communication?
Right.
So that was monitoring. Along the way, we also were able to complement our global clock sync with another really building block technology that we call dynamic traffic control. Because we now know exactly what's happening in your network between GPUs, what we're also able to do is things like redirect flows by intersecting the software layer. So we plug into the communication library that NVIDIA has called Nickel. We plug into TCP communication libraries. We plug into RDMA communication libraries. And when we see congestion, when we see flows contending, we're able to redirect. So the evolution was, with clocks, I can measure things.
Right.
Once I measure things, I can control them. And then how do I now not just exert control at the network layer, but take it up all the way into PyTorch training workloads and really manage the entire application for both fault tolerance and performance as well.
It's fascinating, right?
It's been an interesting journey.
Reminds me a lot of monitoring companies that then add security features on top, because now I know exactly what's coming in and what should be flowing through the network, right?
It's interesting you say that, Frederick. My last company was a company called Sysdig, which began its journey as Kubernetes monitoring at a time when Kubernetes was not even sort of quite mainstream as a 1.0 release. We began just as sort of Kubernetes was coming out. And over the course of the first 5 years, we went from monitoring towards security, from Kubernetes to broader cloud monitoring and cloud security. And so when I looked at Clockwork, I loved the fact, because I remember talking to hundreds of Fortune 500 and Global 2000 companies when I was at Sysdig, where what they really wanted was monitoring to be able to know when something is wrong, but what they would love is remediation, automated remediation,
right,
and very rapid feedback loops. So it's really gratifying to see Clockwork build on the clock sync technology, which allows you to monitor your fabric, all the fleets from GPU nodes all the way down to network, all the way up to PyTorch training workloads. But we don't stop at monitoring. A lot of the evolution has been, how do I then rectify for resilience, rectify for performance bottlenecks, etc.
Yeah. How does that work today? How close are you to being able to automate a lot of this? Like, say I have a network failure in part of my cluster, one of my GPUs goes down.
So what's really elegant about our approach, let's take that example because it's one of the most egregious problems in AI clusters. Most often you see that cluster availability runs in the high 80s to low 90s, and network link flaps are one of the biggest problems. Now, contrast this with the cloud.
Explain what a network link flap is.
Yeah, so typically when you have all of these GPU machines connecting to each other, you're going through an enormous fabric of switches, all of which are interconnected through either optical connections or copper connections if you're within a rack, but optical most likely if you're going sort of a fair distance as you have thousands of machines, right? Now, what tends to happen is that these GPUs are often, because it's an optical connection, any breakdown in the there's a whole chain of really microelectronics that are necessary for packets to travel from one end of the optical connection to the other end of the optical connection. What can disrupt this? You can have overheating because these GPU servers are running extremely hot. And for a brief period of time, the link breaks. You can have dust that comes on top of the actual glass, if you will, and break the connection. You can have cabling mistakes that result in the connection going down. Many of these are transient. And yet, if it's a dust particle that's breaking the connection, unless you wipe the glass or reseat the cable, you've basically lost that link. Now, normally in most cloud applications, protocols, communication protocols and applications have been built to
Right,
be
that's
resilient
the
to all of
whole
that,
point of it, right?
Exactly.
To switch.
Unfortunately, with distributed training and GPU to GPU cluster communication, these communication libraries are so optimized for speed and performance, they don't necessarily build fault tolerance into those libraries themselves. And that's really where Clockwork comes in. What we are able to do through our monitoring and observability product line is detect rapidly when a link is somehow experiencing a problem. But then we go further. You don't need to click a button or push a button or do something to rectify that. When we detect a link flap, we automatically have a watchdog timer that says this has gone on for too long. If I wait a little longer, it's going to propagate all the way up to the application and take the application offline.
Right.
We automatically institute a failover.
Okay.
Not only that, we also wait to see if the link recovers, and when the link recovers, we recover back the original connection. All of this without the application ever knowing anything's happening.
Okay. Where do you sit then in that stack? Where are your sensors? I don't know how to think of
Yeah,
it.
so really good question. Balaji, our founder, is often fond of saying we are a software shim company. And so we essentially monitor all of the fabric from the edge. So we deploy agents on each of the GPU nodes that you're running, thousands of machines, or on your VMs in the cloud. And the agent itself for monitoring is a user space agent that's able to have very deep telemetry while still being a user space application on the end.
So not eBPF, not in the kernel.
The moment you want to control the flows for TCP, for example, we have an eBPF module that plugs in and is able to manage the flow of data through the network. So that's an eBPF module. Now, when it comes to GPU RDMA networks, we have an agent that talks to the RDMA library called IB verbs, and so it's a shim that talks to the IB verbs layer. For fault tolerance, we plug into the nickel or RICL libraries that NVIDIA has for collective communications. So really, this notion of dynamic traffic control is up and down the stack. In fact, we're at PyTorch conference today, and we just announced a product that we're demoing, which is able to plug into your PyTorch libraries and instrument what's happening at the training iteration step boundaries.
Okay.
Look at the entire iteration from beginning to end, from data loader to checkpoint, and break that down and correlate that with what's happening in the infrastructure. So that's a user space application that plugs into PyTorch.
Right. That's different from your usual mode of going to a hyperscaler and working with them. So this is, in somewhat a different layer of...
Indeed. I think the scope that we address, we think of as spanning communication libraries all the way close to the application, down to close to the transport, right? So whether it's nickel, which is for collective communications, or down in the TCP layer and packet layer. So that's really the scope of what we do, is plug into the communication wherever that may happen.
Right.
Interesting you say hyperscalers, because we have one of the top 5 hyperscalers in the world has become a customer of ours. We have multiple neoclouds that are running GPU clusters that are customers of ours today. And some parts of our product, for example, network monitoring, these cloud providers and hyperscalers think of as internal to their own use, if you will. At the same time, some of our products are relevant to the tenants of these clouds, relevant to the tenants of these hyperscalers. When it comes to monitoring the workload, it's something that the tenant cares about. When it comes to making your AI training resilient to failures, it's something that the tenant cares about, not necessarily something that the hyperscaler deploys as an internal use product, if you will. So we sell both to the hyperscaler, but we partner with the hyperscaler and the cloud provider to sell to the end user as well.
Give me an example of what's some of the most common failures you're seeing then? Is it those optical network issues with the flaps?
I would say
flips, sorry.
Indeed. Link flaps are probably, and in general networking is probably the top 1 or 2 problems that we see from a resilience standpoint. It's also one of the biggest bottlenecks to performance. When you have congestion or your oversubscribed networks, or your network might have on average more capacity, but when you have really high bandwidth flows, they collide, etc. Right? So that's one. But if I were to take take some of the other problems. In fact, something that we're working on is how do we extend our fault tolerance that today is able to address network faults all the way to entire nodes failing or entire GPUs failing. So if you now break that down and say, what are the other causes of downtime? I would say memory errors are very common in GPU nodes. I would say NVIDIA's GPUs or AMD GPUs often fail to communicate over the PCI bus. People describe this as GPUs falling off the bus. And there's a whole host of reasons why that happens, but that's a very frequent cause of downtime. I would say what's called XID errors. So firmware on the GPUs somehow breaks down. XID errors, unfortunately, can't be easily predicted, and so they happen all of a sudden. That's a third common cause of failures. Thermal overheating, and therefore the GPU being throttled. So underclocking the GPU, and then sort of over time that becomes hard and the GPU starts to overheat, could be another cause of problems. So I would say those are some of the more common problems that we see across clusters.
How, at this point, you feel comfortable that you can remediate all of those automatically?
So today, what's already shipping, what's being deployed by a lot of customers are really two big pain points that they encounter that we address. The first is network-related problems, whether it's link flaps or entire networks just going off, if you will. And so we remediate those in a way that's non-disruptive. The second one is performance bottlenecks in your network that slow down your application. We remediate that. As far as the other faults are concerned, our observability is not just network observability. We are able to observe things like temperature overheating that I described. We're able to observe things like there are too many memory errors that we're starting to see, and that means the GPU is sick and eventually it's going to die. And so monitoring the health of the nodes in the fleet is also something that we already do. But in terms of remediation, as I mentioned, what we're working on is the ability to say when an entire GPU goes offline or an entire node goes offline, how do you take a pre-provisioned spare node, bring the spare into your working cluster, and still leave the AI training uninterrupted, if you will. So that's sort of where we're heading over time as we think about our roadmap. And so fault tolerance to any kind of GPU and node failure, irrespective of what's driving those failures, some of which can be predictive failures, some of which are unplanned failures. That's where our roadmap is taking us.
That's interesting, that standby, because often when you do these snapshots you need to have the exact same hardware again to continue from that spot, right?
Right. In fact, you said something really interesting, Frederick. So when you think about why is resilience so hard in these GPU clusters, right? It comes down to distributed state, right? So the first aspect of state is what's happening within that single machine when I'm running lots and lots of CUDA kernels, when my CPU is running certain things. Can I snapshot the state of the machine into a consistent state? And that is a difficult problem, but tractable because it's about a single machine and its state. What is a lot more intractable is it's not enough for me to capture the state of that single machine. My AI workloads are always about distributed state. We were talking a little bit about what makes fault tolerance so hard in these GPU clusters, right? And so, and I think you mentioned snapshots. So the thing we have to realize is that when you think about AI workloads, the challenge is about how do you capture distributed state. So if you were dealing with a workload that's just running on a single machine, that single machine itself is complex because you have hundreds of CUDA kernels and CPU processes that are running at the same time. But at least the problem of how do you snapshot the state of that machine is somewhat tractable. But the moment you realize that machine, when you snapshot that machine, you also have to figure out how to maintain a consistent state. And that machine may be talking to 100,000 other GPUs. So you have to simultaneously maintain state across all of these GPUs. And that's really where the communication problem becomes really meaningful. The fact that we understand distributed communication is what's allowing us to say, how do we build fault tolerance by understanding the distributed state of the entire cluster and allowing the application to continue when one of the nodes in the distributed sort of cluster is somehow in a faulty state. If you
How much AI are you using in the process there yourself?
It's a very, very good question. We have a exciting project that we're working on. We have such a wealth of data from an observability standpoint. And yet for most customers, the idea that I can basically understand what's going on in my system by looking at all of these dashboards, etc., as elegant a UI as we've built, it still takes a lot of knowledge to be able to really understand what these dashboards are telling you. Right?
Yeah.
And so something that our founder is extremely passionate about is how do I convert all of this data into spoken language interactions with our customers where you should be able to say, tell me what's going on in my data center XYZ, where I seem to see that jobs are somewhat slow, right? And so really that's where our first use case for AI is around how do we take our observability data and manifest all of that data into a very easy to engage with AI bot.
Yeah, which I hope has almost 100% uptime because you're using your own technology to keep that going.
And this is, I think, the entire industry is starting to think about user interactions as gradually migrating more and more to chat interactions. And so that's a very natural place for us to leverage AI.
Absolutely. Well, let's talk a little bit about the industry in general as well, because without putting a date on anything, but you've been around since the 90s at NetApp and Sysdig and what's the storage? Nimble Storage, exactly. You said something interesting earlier on that when we were talking offline, that this time feels similar to before the dot-com bubble burst.
Right. And yes, so specifically I was reflecting on the excitement I felt in the late 90s when I felt like we were creating powerful outcomes in technology. The technology itself was really exciting. The speed at which things were moving were really exciting. The imagination that people had for what the world could look like with all of the sort of internet emerging was exciting, right? In fact, I have to say I was at Sysdig up until last year, and there was a part of me that thought I was going to retire after I was done with Sysdig. But Sysdig started using AI in its own products, and we've built some really good agentic technology within the Sysdig platform itself. But that opened my eyes to what I think the next decade is going to look like. And that's what sort of got me excited about engaging with Clockwork. What we were doing was optimizing infrastructure that was being used by some of the largest AI builders in the industry. And so that excitement is very similar to what I felt in the late 90s. I feel like a sense of what the technology space is going to look like over the decade I think AI will reshape everything, and it's almost a truism at this point to say that. So that's one dimension that I was commenting. Now, the other dimension is, of course, talk of a bubble is now increasingly around us.
Yep.
And when I think about valuations, it may be true that sooner or later we're going to experience the stock market cannot be this frothy. Mm-hmm. I do feel it's different from the late 90s as well, though, Frederick.
Okay. I hope so.
Yeah. So there's one thing. This is what I was commenting on. When you look at the revenue of perhaps the single biggest company shaping AI is NVIDIA, and when you look at the revenue stream for a company like NVIDIA, 80-90% of that revenue, or north of 80% of that revenue, is coming from a few really large hyperscalers.
Sure.
And if you look at the capex of those hyperscalers, on the one hand, you can say that capex is enormous and scary. On the other hand, it's not that much more than their annual operating cash generation. And so a lot of the revenue of many of the companies in the AI space is coming from operating cash, not from investors funding .com companies in the late 90s, right? And so that's one thing that I think is very different from what I experienced in the late 90s. I was at NetApp, we were growing extremely quickly. When the .com bust happened, we went from $1 billion to $800 million. So we lost 20% of our revenue in literally months, it felt like, right? Annualized revenue. Maybe that will happen again, but I don't think it'll be as big. I do think the stock market correction could be substantially larger, but I don't think the revenue will disappear. Mm-hmm. And to some degree, there's a part of me as an observer of technology that says, whether the bubble bursts or not, it doesn't matter, right? In fact, most great technology changes will probably go through some of these upheavals when it comes to stock valuation.
Sure.
But I think the progress of the underlying technologies will continue in a very rapid clip over the next several years.
And I always hesitate to ask about the next several years.
I
but
know, especially at the
even
pace
if-
at which.
Even if you're just looking at a year right now, seeing what you're seeing, you're talking to the hyperscalers. You probably know more about what's coming than most of us. But what do you think will happen in the next year? Where will we be in the next year?
I think that the good news, if we want to think about it this way, in the context of investments and the progress of AI, is that given the supply constrained industry we've been living in, most of the demand for 2026 is already spoken for in the form of contracts by the hyperscalers with a lot of the infrastructure providers. So on the one hand, you worry about have we overhyped the space. On the other hand, in terms of real revenue and real flow of infrastructure, deployment of infrastructure, most of 2026 is already spoken for by many of the large providers. As a result, a lot of the software innovations that are powering AI, whether it's models making forward progress, and now vision models and multimodal models, all the rage, if you will, and then their use in agentic AI use cases, I don't think that will slow down. That will only accelerate even more. Candidly, I'm scared when I look at sort of what I see in Sora 2 or some of the more recent sort of models. And so having come from a security background, there's a part of me that just says we will have lost all ability to tell the truth from falsehood in the not too distant future.
This whole conversation was generated by Sora.
Exactly. It could be entirely generated.
Don't know.
Yeah. So if I have to say, so there's an optimist in me that says technology will progress. If I am pessimistic about something, or it's not even pessimism as much as uncertainty, I worry about people that are in the job market in their 20s right now, because I think that is the place where I hope that 5-6 years from now it'll have reached a new equilibrium, but I always worry about the dislocation when these changes are happening. And I think over the next 4 to 10 years are going to be really interesting for people in the job market. I think we'll see a seismic shift in what jobs will get created, but also what jobs will face upheaval.
I agree. Well, on that positive note, thank you, Suresh.
Thank you. It's a pleasure.
Same here. Appreciate it. Same here.